there's half the class missing. People who don't come to class get lower grades. So feel good you came to class. Everyone else will be dropped to half a grade who doesn't show up. Okay. Okay, today we're going to talk about the non-adiabatic non-isothermal plug flow reactor. Remember last time, before we did multiple steady states, we did a generic balance that more or less looks like a balance for CSTR because you didn't see any integrals there. You only saw algebraic equations. As I mentioned, generically, what we would like to do is we would like to use the design equation to solve, which is a mass balance, to solve problems, to do our design of our equation, of our reactor. But because the rate is a function of both the conversion as well as the temperature, we can't integrate dx, where x is the conversion, unless we know t is a function of x, because t varies. So ideally what we would like to do is we would like to write down the heat balance to relate t and x, and solve the heat balance, plug in for t of x, and then the rate only depends on x, and then we could solve the design equation. And the problem is, in real life, that's rarely the case that you can solve those equations sequentially. Usually you have to solve those equations together, because typically the rate depends on the concentration as well as the temperature. And when you solve the heat equation, you need to know how the rate varies with concentration in order to solve the heat equation. And in order to solve the design equation, you need to know how the rate varies with temperature. So you have to solve them both together, and we're going to illustrate this in this problem here. The most common type of reactor that we use is a fixed bed reactor in many chemical processes, particularly in petrochemicals. Now, of course, if there are more or less three ways of running a fixed bed reactor. In one method, you could keep it adiabatic. That is, you can insulate the fixed bed reactor, and therefore the temperature, the heat that's generated or consumed by virtue of reaction goes to either heat up or cool down the reaction mixture. And then clearly the temperature is a function of conversion. A second method is if you take the insulation off and you expose the heat exchanger to the environment. So in addition to heating the heat that's generated or consumed by the reaction, in addition to that heating or cooling up the feed, it also exchanges heat with the environment. Now, you can imagine that that might actually not be a bad thing. Why is that? Well, if I have an endothermic reaction, then as we saw last time, when you have an endothermic reaction, as the reaction proceeds, the temperature of the reaction mixture decreases. And that means that the rate slows down. Remember, our ideal temperature profile was vertical, where we kept the temperature fixed. So if we're dealing with a situation where the reactor temperature is lower than the ambient temperature, than the outside temperature, then as the reactor cools, it then will draw in heat from the surroundings, UA delta T. And that'll be good because that'll move the temperature profile closer to the vertical. Similarly, if we have an exothermic reaction, and if the temperature starts to rise very high, then usually what we're afraid of is that at some point along the reactor, the temperature will get so high that it'll go beyond the maximum temperature that the materials can sustain, and it will cause damage. As a result, when we take the insulation off, then as the reactor starts to heat up, it'll start to lose heat to the surroundings. So that'll add that'll add some cooling to the reactor, which might mollify the maximum temperature that it can attain. So both of those are not bad. Both of those are pretty good. And typically the first thing that goes when the reactor gets too hot is the catalyst. Typically, when you have catalytic reactors, say in a fixed bed reactor, the catalyst bed is fixed. When the temperature gets too hot, it starts to kill off the catalyst. We'll talk a little bit more about catalysis in the next couple of weeks, but basically, typically catalysts are little particles, typically on the order of a millimeter, could be smaller, could be a little larger, that are very, very porous. And then there's some transition metal that is almost in single atoms distributed throughout the pores of this catalyst. And typically the catalysts, at least in the petrochemical industry and the transition metal catalyst, typically it's the interface between the metal and the support. The support is often alumina, Al2O3 or something similar. Typically it's those interfaces between the metal atoms and the alumina support where the reactant can actually bind and react. So you want to distribute the metal as widely as possible, as thinly as possible, so you have a lot of this interface. What happens is when you heat up, when the catalyst gets too hot, then the metal atoms start to move and they start to agglomerate. So you have a lot less of this interface. But the other thing that can happen is your catalyst support, the alumina or whatever it's made of, has lots of little sharp little points and edges where the metal could sit. And what happens is when it gets too hot, then sometimes they can sinter. They can sort of singe. And then again, they no longer have catalytic activity. So that's sort of some of the potential mechanisms by which when the reactor gets too hot that you kill off catalyst.
What kind of temperature ranges are you talking about, just in perspective?
It all depends on the catalyst.
Like for the alumina and the
It depends on the catalyst. I can't give you a number offhand. I don't have one on the tip of my tongue. It all depends on what kind of support that you use and what the catalyst is. But it varies widely.
I have temperatures for the aluminum catalyst.
That's okay.
Is it below the melting temperature of the metals itself? Would it be?
Yeah, it's well below the metal. Well below. If you were melting, it would be. Okay, so now sometimes the cooling by heat exchange with the environment, the heating and cooling is insufficient, and I need additional cooling. I'm really interested in the attendance sheet today. Make sure you sign it because half the class is not here and they're going to be sorry that they didn't make it. Okay, so sometimes we need extra cooling and we have to have an additional Q. Okay, so if we need a heat exchanger, and if we have a reactor, we need a heat exchanger. So there's a heat exchanger on the outside. Then to design a reactor like this could be quite complicated because if the heat exchanger is on the outside and if the reactor is not sufficiently thin, then I'm also going to have gradients between temperature gradients between the center of the reactor and the walls. Now, if I have temperature gradients, I'll have gradients in reaction rate because the hotter temperature is going to react faster, the colder temperature is going to react slower. And in addition, the hotter temperature may have, if it's an exothermic reaction, for example, the hotter temperature will have equilibrium limitations that are more stringent than the lower temperature. So if I have temperature gradients from the inside to the center of the reactor to the walls, then I'll also have concentration gradients. And with a heat exchanger, this is very difficult to design. If I have T as a function of R and Z, and the concentration is a function of R and Z, then these reactors are difficult to design. Doesn't mean impossible, but they're difficult. So what we're going to do in this case, the example I'm going to do today, is a one-dimensional case. So this is hard. So the example I'm going to do today is one where I have a reactor that's sufficiently thin and I have passive cooling. I exchange with the environment as characterized by an overall heat transfer coefficient U. And because the reactor is thin, then that means that T is only a function of Z and not a function of R, and C is only a function of Z and not a function of R. And one thing that you should note is I should be precise about what I mean by thin, and you should be precise what we mean by thin. And if you remember in Transport 2, you had that last semester, right? Transport 2, you did a problem of a cooling fin. Remember you did that problem? Formatted hard drive?
We didn't do that problem.
You didn't do the problem of the cooling fin? You have a hot surface, and then you put a little fin here, and then you get some cooling this way. So you have conduction this way. The heat has to conduct out this way. And then you also have Newton cooling to the environment. You didn't do this problem? I'm going to check. Who taught that course? What book did he use? This is in Bird, this problem. Anyway, in that problem, you look at the temperature. So you have, this is sort of like a radiator, the radiator in your house. You've got the hot radiator, and then if you look at the radiator, it typically has these fins. And that's to increase heat transfer. Now, of course, the fins usually come to a point, but if you ignore that, you assume it's rectangular. Then typically what you assume is that the temperature, you solve the heat transfer problem in this region. And you've got two directions. You've got X, and Y. And typically, so in principle, the temperature should be a function of X and of Y in this case. But if the fin is thin, well, what does thin mean? Thin means that basically it means that the conduction in this direction is fast compared with the heat transfer of the Newton cooling. So thin isn't an absolute thing, it's a relative thing. So, and you come up with a dimensionless quantity involving K, the thermal conductivity, the thickness here, and H, the Newton cooling coefficient here. So their thin is a comparison between essentially how fast the heat transfers from the center to the edge and how fast it transfers from the edge to the atmosphere. And as long as the rate at which it transfers from the center to the edge is fast compared with the rate at which it transfers out, then you can neglect the Y dependence. Similarly here, as long as the rate at which, it's the same idea here, as long as the rate at which the heat, which is produced by reaction, transfers from the center to the edge, so it's a dimensionless quantity that's going to involve the radius of the tube. As long as that is fast compared with the rate at which I have cooling, here it's in terms of U, then I can ignore the R dependence. And I'm not going to make that precise here. I'll let you do that. Now I'm just going to assume that. So I need so are there any questions on the setup of the problem? Okay, so I need to just make some issues about the notation. If you remember previously when we were doing this hand-waving heat balance, I had a CP prime and a CP double prime, which this was the total heat capacity of all of the reactants, and this was the total heat capacity of all the products. Now, of course, I lumped all that in there because this was just sort of a hand-waving balance. Today what I'm going to do is I'm going to assume CP of the reactants is equal to CP of the products. But I'm also going to do this with CP hats. So these are per unit mass. So whereas these were total CPs, these are per unit mass, which is what we usually do. Usually in chemical engineering we use CPs per unit mass. So that way we have the mass flow rate explicit. And what we're going to do is we're going to do a steady state balance on a reactor where this is a non-isothermal, non-adiabatic flood flow reactor. We can think of it as a fixed bed. And I have a distance Z, and this is Z is equal to 0, Z is equal to L, and at some point in the middle where I'm going to do my mass balance, this is the distance Z. And this is a thickness delta Z. And I'm going to have the temperature, a temperature and a concentration at Z, and also a temperature and concentration at C plus delta Z. And I also have an inlet and an outlet. And again, I'm assuming that things only depend on Z. Now, in addition, I have a volumetric flow rate, V, volumetric flow rate, and this particular, and I have a cross-sectional area. And delta V is the cross-sectional area delta Z, and A is just pi r squared, where r is the radius. So nothing fancy there. A is pi r squared, and that's of course the cross-sectional area. So now what I'd like to do is I'd like to do a steady-state mass balance. And I want to do a mass balance and heat balance on this reactor. Are there any questions on what we're going to do? We're going to do the balance on dV. On this note. All right, so let's start with the mass balance since that's easier. What is the general equation of chemical engineering? Rate of accumulation. Okay, so let's do a mass balance. And let's do it on this delta Z. On this delta V. So this is a steady state mass balance, so I'm going to neglect this. So for mass, as a mass balance, I have 0 is equal to in. Well, in, what is in? The in for species A. Concentration, since I'm only worried about species A, I'm going to do Ca. C is just going to be Ca. So in is what? What is the moles of A per unit time entering this little beacon?
Ca at Z.
That's the wrong units. What are the units of Ca and Z?
Moles per bar.
I want moles per unit time. How do I get moles per unit time?
Times V.
Multiplied by flow.
Multiply by the, so I've got Vc evaluated where?
At Z.
At C. And out?
VC evaluated at Z plus delta Z.
Z plus delta Z. Plus generation.
Generation would be delta V times the rate of reaction.
Delta V times the reaction rate. Now, R rate. So this is the rate of production of A. If A is a reactant, then this is negative. If it's a product, it's positive. Times delta V. So I can rearrange this, and delta V, I can note. Actually, I can make this delta V, and then I can make this at V and V plus delta V.
Oh, okay.
Where Z, V is Z times A. Okay, so now I bring these two to the other side, divide by delta V, and what do I get? I get, so I have VC dV is equal to RA. Now, if V is, okay, where RA, we remember, is a function of C and T. If I have constant density, and do I want to make the constant density assumption here? Yes, I do. If I have constant density, so at constant density, I have V dC dV is equal to RA of C. Now I want you to notice, if this is all I had, if I didn't have any temperature dependence, then this would just give me this would just lead to the design equation. Why is that? I would move dv to this side of the equation, I'd move v to this side of the equation, and I'd move r to this side of the equation. And when I integrated, I would get big V over little v. So if I did that, I would get dv over little v, which I would integrate to get v over little v, which is tau. And then I would just get dv over Ra, which is just the design equation. But I can't do that here because I can't do the integral because Ra is a function of c and t depends on c.
Shouldn't it be DC on the right?
Yeah, dc. But I can't do this here. This is because Ra depends on t and t depends on c. So until I know t is a function of c, I can't do that. If I knew t is a function of c, I could do this. All right, so let's do the energy balance now.
Question.
Yeah.
I thought T was a function of C, but
It is, but and z is a function of c. Or c is a function of z. So I can eliminate z and make t as a function of c. So we're both right. Okay, so now let's do the heat balance. So again, steady state. What is the heat going in here? What's that?
Q.
The flow. Here, there's no external Q. The only Q I have is, I'll talk about, is U, the passive cooling. But I'd like to know by virtue of the flow mixture, what is the enthalpy in? F? What is F? Do we use F in this course? Did you just appear in this course? What notation have we been using since January? I'm sorry, since September, August. Have you ever been to this class before? Behind you? CP. CP hat is per unit mass. So what's missing? This is a volume per unit time. This is energy per unit mass. No clue. What's missing? This is basic chemical engineering.
Times the density times Tm minus T ref.
T minus T ref. And this is at Z. The last four people who had no clue do not belong to do not belong in the senior class. Let's go back to being sophomores. What is out?
The density times V times CP, T minus T naught at Z
Huh?
plus Z plus delta Z.
Z plus delta Z. Here I'm doing a V plus delta V. Is there anything now? If I have passive cooling, then I also have cooling by virtue of U. So what else would I have in out?
If you have cooling by U, then it's like the Q, so it's minus U.
So I have minus U. U is the heat transfer coefficient. What is that multiplied by?
The area, if it's
What is the area if it's a cylinder?
2PR.
2 pi r times
Delta Z.
2 pi r delta Z. Okay, well, if I want to write this in terms of dV, dV is pi r squared delta Z. So if I multiply by dV over pi r squared delta Z, the delta Z's cancel, an r cancels, and a pi cancels. So I have 2 over r dV. What's missing in that factor, in that term? Is still something else? UA times, what is delta T? T minus which T?
T on the outside.
No.
T on the outside.
T on the outside. T minus T surroundings. T naught is the reference state. We haven't chosen a reference state yet. Okay, and now plus generation minus consumption. So generation is by virtue of what process? The reaction. So I have generation. I have is by virtue of the rate of A is being consumed. So let's say A is a reactant. So I need what do I need here? The rate with a plus or minus? Minus RA. What is that multiplied by? I'm doing an enthalpy balance. Calm down. You're shaking. The heat of reaction with a minus or a plus? Heat of reaction is the heat absorbed. So here we want heat produced. So should it be with a minus or plus? 50-50 chance. So minus, because we want the heat liberated. The delta H is the heat absorbed. So the minus that is the heat liberated. Okay. And now what we're going to do to make life a little easier is we're going to take the surrounding temperature as the reference state. Choose any reference state I like. So this will be T0. Well, actually, I'll do that a step later. So here we have one equation, the mass balance. And now we're up to the energy balance. Yeah? Probably, yes. Thank you. Yes, thank you. And I should have known that because this is the heat per unit mole of reaction, and this is the moles per unit volume time. So that just gives me heat per unit volume time, and everything else is energy per unit time, so I need a volume. And thank you for pointing that out. Any other questions? Okay, so let's now bring these two guys to the other side of the equation, divide by dV, and take the limit as dV goes, delta V goes to 0. And if I do that, again at constant density, I get rho V Cp hat ddt or dV T. Because the T0s cancel out. And that's equal to minus RA of C T of C. Actually, let's do it the other way around here. This is T and C of T times minus delta H minus 2 over R U, 2 over R U, T minus T surroundings. This is the mass balance, this is the energy balance, the enthalpy balance. This is what we would have called the design equation a few weeks ago when we were still naive babes in the woods. We didn't know about, when we didn't know about non-isothermal reactors. Now we're much wiser, older and wiser, so we know about them. And we notice that in order to solve this equation, in order to solve for the concentration, I need to know how to do the temperature at different points in the reactor. I need to know T as a function of E. In order to get the temperature, I need to solve this equation to get T as a function of E. But to solve this equation, I need to know C as a function of T, or C as a function of E. But to get this, I need to solve this equation. So I can't solve them sequentially, I have to solve them together. Now, you could imagine we have computers today. So we can just put it up on a computer, whatever that means, and write a program and try to solve this. But before they had big computers, people wanted to solve things also. And a lot of times, you can, a lot of times, by using some physical insight, you can understand the solution to a problem before you get to a computer. You can get a lot of the main results or main that you will get from the numerical solution just by understanding the physics of the problem. And alternatively, if you understand the physics of the problem, you understand much better how to write a numerical routine that will converge orders of magnitude faster than if you just try to use a generic routine. Okay, so let me first give you, graph something of what happens when you just solve the problem. And that'll give you a sense of what the issues are. And the reason I'm doing that is because if you were real engineers already working in a plant, you wouldn't need the numerical solution to know what the problem was. You would have seen the problem in the plant. But since we haven't worked in a plant, most of us haven't worked in a plant yet, it's good to see what the solution is going to look like so you'll see what the problem would be. All right, so what does the solution look like? And this is the solution for the temperature as a function of z in degrees K as a function of z for naphthalene oxidation. Which is a highly exothermic reaction. Naphthalene oxidation is highly exothermic. So what do you get? Well, this is a gaseous reaction in a fixed bed reactor. So by varying the total pressure, or if you like the partial pressure of reactant, of naphthalene, then you change the concentrations, and if you go to higher concentrations, the reaction goes faster, and it heats up. Okay, so at low concentrations of naphthalene, the curve looks like this. At higher concentrations, like this. Like this. And I'll put some numbers in for no particular reason.
T.
So I want you to notice what's going on here. At very low concentrations, there's no problem, but there also isn't very much reaction, so I haven't produced very much. Once I get to higher concentrations, and look how little the concentration changes between here, here, and here. Between 0.017 and 0.019, I have drastically different behavior. But what you see at 0.017, 0.0182, is that the temperature goes through a maximum. So the first characteristic here is there's a T max as a function of z at a particular z max. And that's the real dangerous spot. If T max is too high, I can fry the catalyst. Well, frying the catalyst is a bad thing. Costs money. However, if I go from 0.0182 to 0.019, look what happens. This curve just keeps going way up. And there, now you could get into a dangerous situation where you could have an explosion. So, and there isn't very much of a difference in the partial pressure between these situations. So what this curve points out is that being a chemical engineer, designing a reactor, is a dangerous business. You really have to know what you're doing if you have exothermic reactions. If you have a very exothermic reaction, that's known as a bomb. So what you don't want to do is make a bomb. You want to make the product of naphthalene oxidation. Speaking of bombs, there was a long time ago, there was the first attack on the World Trade Center. It was about 1994 or 1993. And so I don't know if anyone has ever looked up those articles, but two people rented a truck and they drove into the garage underneath the World Trade Center with a rough bomb made out of fertilizer, nitrogen. And then they left and they detonated the bomb. And luckily the bomb wasn't big enough to topple the tower, but it caused a lot of damage and a few people were killed. A couple of days, now of course, the guys who did this weren't the smartest people in the world because they put a deposit on the truck and they went back to the rent-a-car company to get their deposit back. It was pretty easy to catch them. So they were caught. And then the headline, and it turned out that they were chemical engineering students at Rutgers. And the headline in the New York Times the next morning was, "Chemical engineer held in Trade Center bombing." So they were trying to make a bomb. They actually made a bomb. Luckily, it didn't do as much damage as they had hoped. Okay, so anyway, what you can see from this picture here, from this graph, or what you could see, what you hopefully don't want to see in a plant, is a situation like this. You want to head it off before it happens. But now that we're aware of what might happen, we realize that this picture has a lot of information. It's the simultaneous solution of both of these equations. The most important piece of information we have that we need from here, and what we would like to get before solving the equations numerically, is what is the most important piece of information, the absolute most important piece of information? Volunteer? Tmax. How high Tmax is and where Tmax is. I need to know where it is because that's where I have to put the coolant. And I want to make sure that Tmax is below the maximum allowable. So what we're going to do, we're going to come up with a method to estimate Tmax. And to estimate Tmax, we're going to have to think about the physics. Tmax, Zmax. And we're going to do this by developing an understanding of the problem. At least that's the goal. I'll develop an understanding of the problem. Hopefully you will too. Okay, so let's think about the reactor. Here's my reactor. And let's say at some point I have a Zmax, where T reaches its maximum. So I'm going to divide the reactor up into two parts. And I'm going to assume, well, I don't even have to do that. I have a T surroundings. T0 actually canceled that problem. Okay, so, oh yeah, I'm going to assume that the inlet temperature of the feed is the same as the temperature of the surroundings. So, which is not, it's something I can control. So I'm going to assume the way I run the reactor is that the inlet temperature, T inlet, is equal to T surroundings. So I'm going to fix that. Okay. Now, what initially, when reactant comes into the reactor, the temperature of the reactants and the temperature of the surroundings are the same. So this term is tiny. So initially, when the reaction starts, there's no heat transfer. And the reactor thinks it's adiabatic. Is that clear? Because T inlet is equal to T surroundings. Now, of course, as you proceed down the reactor, the reaction happens and the temperature goes up, so you eventually start getting some heat transfer. But I'm going to make a drastic assumption, simplification. That Z less than Z max, until I get to Z max, implies the reactor is almost adiabatic. That's certainly true near Z is equal to 0. It's not true near Z is equal to Z max, and the closer I get to Z max, the worse it is. But we're making simplifications here. Okay, that's for the first part of the reactor, this part. The second drastic simplification is for Z greater than Z max. Well, what happens for Z greater than Z max? if I get to the end of the reactor, over here, at the end of the reactor, there's no reactant left. The reactant's all used up. So the rate of reaction is tiny. Moreover, the reactor is really hot. After Zmax, the reactor's really hot. So this term gets really big, and this term gets really small. So let's make the assumption that this term is 0. So here we're going to say reactor almost purely heat transfer. Now again, we know these assumptions are wrong. However, in a couple of minutes I'm going to argue to you that these assumptions are conservative. That doesn't mean that they supported Romney. They're conservative, meaning these will give you an overestimate of Tmax. So if you make these assumptions and you calculate a Tmax that's okay, that's not too hot, the real Tmax will be less. So that's an okay assumption to make. It's a conservative assumption. And you can kind of see why that's the case. You can see why this is going to give you a Tmax that's higher than the real one. Because really, the reactor isn't adiabatic. So really, there's some heat loss. So by assuming it's adiabatic until here, you're heating the reactor up more than it really does. So you're going to get a higher temperature than in real life by doing this. So your Tmax that you're going to come up with is going to be a little higher than real life. That's okay, is if I can control something higher than Tmax, then I've controlled Tmax as well. So that's why it's okay to make these assumptions. If it were the other way around, then it would be a stupid argument. You know, great, I controlled something less than Tmax. Tmax blew up the reactor, but you know. Okay, so that's the basic assumptions. And let's see what happens when you do that. Let's do the analysis. Well, actually, there's one more thing. So, and where does Tmax occur? Note, Tmax occurs when dt dV equals 0, and dt dz equals 0. That's what the maximum. And when dt dz is 0, the heat transfer balances the heat generation by reaction. When heat generation equals heat transfer. Well, here I have heat generation because it's adiabatic. Here I have heat transfer. So what I'm going to do is I'm going to plot the heat generation due to this. I'm going to plot the heat transfer due to this. And where they cross will give me an estimate of Zmax. So that is, this thing, I'm going to plot heat generation from the adiabatic curve. Heat generation meaning as a function of Z. So from the heat generation, I'm going to get T of Z. From purely adiabatic, I'm going to get a T of Z for Z less than Zmax. And then I'm going to plot heat transfer only, purely heat transfer to get T of Z for Z greater than Zmax. Now you might say, I don't know where Zmax is yet. We'll see, don't worry, we'll get there. Okay, so let's do the analysis for Z less than Zmax. For Z less than Zmax, this term is gone. So now I'm going to take this curve, this equation and divide, well, this equation and divide it by this equation without the U. So when I divide, the V's cancel. I've got rho Cp, and the dV's cancel, if you like, because these are total derivatives, dt dc. Is equal to,
The V's cancel.
I'm sorry?
The V's cancel. The V's cancel.
The V's cancel, and the dV's cancel. Oh, rho Cp, I'm sorry. Thank you. Rho Cp, have dt dc. See? And when I divide this by this, I just get a minus delta H. A minus delta H is a plus delta H. Hopefully I didn't screw up the sign. So this just tells me something simple. This says that T minus T inlet is equal to, which do I want the constant on with the C's or with the T's? C's. Yeah, I want it the other way around. Okay, so T minus T inlet, I've got a rho Cp hat over delta H is equal to C minus C inlet. So this says that the concentration, that the temperature goes up, the temperature and the concentration go up linearly with each other. And I think I probably screwed something up because there's probably a negative sign somewhere. The concentration's going down and the temperature is going up. So I probably want a minus here and then put the minus here. Cn minus C. Because this is an exothermic reaction. So I want delta H is negative, so minus delta H. So I just multiplied by minus 1 squared. I put this minus 1 here and minus 1 here. Okay, now this is positive, and in particular this is C of Z. So I see that T and C are linear in each other. Okay, so now what I'd like to do is I'd like to plot the heat generation versus T. Heat generation versus T. Okay, so heat generation, what is heat generation? Heat generation is minus RA times minus delta H. Can you see the blue chalk? Can you see the blue chalk? Okay. Okay, so I'll find another color that you can't see. Okay, so RA is going to be K, some sort of rate constant, times some function of C. Times minus delta H. Okay, and let's try to plot what this looks like. You can, of course, calculate it. You just plug numbers in a calculator, but it's sort of straightforward. And notice that the temperature is linear in the concentration. So what happens? Initially, I've got a low temperature, so K is small, and a high concentration. F2 of C is big. But since K is small, the product is small. And then as I move along the reactor, remember this is adiabatic, so as I move along the reactor, C starts going down. It goes down a little bit. When it goes down a little bit for small z, T goes up a little bit. But K is exponential. So the exponential growth here is much more important than the linear decrease here. So it starts going up nearly exponentially. And then at some point, so it starts going up exponentially, and then when I go way down the reactor, there's no C left. K is very high because T is high, but there's no C left. It was adiabatic. So I know it's got to come back down. So I know immediately that the curve has to look like this. It's got to go up, and then it's got to go down. It has to look like that. Let me draw it again. I just don't like the way I drew it. Now this is the adiabatic curve. The true curve, I want you to keep in mind, the true curve is not adiabatic.